Marcy, Dick,
I should
Mark
should have made myself a cup of coffee.
Yeah.
You guys, just as an FYI to everybody, I just turned on recording for the meeting so that we can play this back to anybody anytime we want. I just wanted everybody to realize you're being recorded. So if you'd like to turn your video off, go ahead.
Thanks, Barry.
Richard and Marcia Glass are here.
Okay, great. I guess
Hi,
we'll
Ben, how you doing?
maybe another minute or two. But we're very glad to have all of you joining us today.
There's lots of pillows on this chair.
Oh, okay. You're not in it.
Well, thank you for your patience. We're still kind of working at we're kind of new to Zoom presentations at Snow Canyon, but we're getting it figured out slowly but surely. And I think what we'll do is I will go ahead. My name is Kathy Edwards, and I'm the president of Friends of Snow Canyon this year. I'd like to welcome everyone to this is our second Zoom presentation for members. And tonight we are very pleased to have our newest board member, George Otott, is going to be talking with us about the origin of the Navajo Sandstone. George worked in the petroleum industry for his career. And then he and his wife moved to St. George area in 2017, and they're involved in a number of things and taking people on Road Scholar trips through Dixie State or through the Road Scholar program. And so I'll turn the time over to George. Oh, and George, you're muted right now.
Host needs to mute everybody, please.
George, there you go. George just went live.
All right, good. Okay. Buddy, thank you for attending my presentation on the origin of the Navajo Sandstone. So basically, I'm going to, describe the rocks briefly in Snow Canyon, and then I'll go through a series of question slides, and we'll talk about the origin of the Navajo Sandstone. I want to preface by saying that my presentation is based on what we call paleogeographic maps, which means ancient geography maps of the Earth millions of years ago. So they will show the location of ancient seas, mountains, dunes, rivers, and plains, and are intended to portray the changing landscape that occurred in North America, the US, and the Four Corners region from about 220 million years ago to the present time. So please keep in mind that for most of my presentations, the mountains that you will see on the maps have long ago eroded away, and the seas, rivers, and plains have long ago disappeared. So with that, I will move on to my first slide. Okay, can you see that? I'm having a little trouble getting a response. Okay. Okay.
Yeah, you switched onto your first slide. It looks good.
Okay, very good. So the rocks in Snow Canyon, the short answer is lava, sandstone, and siltstone. So what I'm going to do is I like to start with a bird's eye view of Snow Canyon that I lifted from Google Earth. And on this aerial photo, you'll see the outlines, the border in yellow of Snow Canyon. And Ivan's down at the bottom of the view, and Red Mountain prominently on the lower left-hand corner. So I'm going to start with the youngest formation in Snow Canyon, and that's the Santa Clara lava flow. So it's 33,000 years old, so it's very, very young by geological standards. And the flow emanated from a cinder cone up on Route 18, flowed into Snow Canyon, and flowed all the way to Harmons, or almost got to Harmons. Anyway, this lava flow is a basalt lava flow, and it's has flowed the sandstone rocks in the canyon, and it was named after the Santa Clara River. Much older than the Santa Clara lava flow is the Navajo Sandstone, here highlighted in orange. And I like this view because it shows clearly how the Navajo Sandstone dominates the landscape, not only in Snow Canyon, but in nearby areas. So the Navajo Sandstone is composed almost entirely of sand. In this area, 1,500 feet thick, and it was named over 100 years ago by a geologist after Navajo County, Arizona, and he was the man that first described this formation. And older than the Navajo Sandstone and lying below it is the Kayenta Formation, highlighted here in yellow. So the Kayenta Formation is 700 feet thick, and it consists mostly of very thinly bedded or thinly layered siltstones and very fine-grained sandstones. And you'll notice it outcrops only at the entrance to Snow Canyon State Park. So it's not widely known about. I think most people go in and out of it and never even notice that it's a different formation. All the other landscape you see, Ivans and the bottom of the washes, and even on top of the lava, covered by thin layers of very recent sand, wind-blown sand, and other sediments called alluvium. So now what I'm going to do is I'm going to make a cross-section, a slice of the earth. It starts just to the east of Snow Canyon, and it progresses all the way southwest through Red Mountain and to the Santa Clara River, just to show you how the different formations relate to each other. So the landmarks on this cross-section, and by the way, the cross-section is a very useful geological tool. It's called a stratigraphic cross-section to illustrate the relationship of the formations. So the Navajo Sandstone that we talked about is at the surface, and you can see it's heavily eroded. So much of it has been removed by rain and weathering. And the little black indentations are the various lava flows. Some of them have been filled valleys that were cut into the sandstone by ephemeral washes. And then at Highway 18, that lava is a bench. It's actually an inverted valley. I noticed you had a presentation last year on a walking tour. A lot of you probably heard a lot about the lava on that presentation. Below the Kayenta Formation are some really fascinating older formations that we're not going to talk about today, but they're splendidly on display throughout southern Utah, southwestern Utah. So how old is the Navajo Sandstone? Well, it's 190 million years old to 180 million years old, meaning it was deposited originally during that time frame. So before we start about that, about talking about the time, what I like to do with in my presentations is talk about geologic timescale, because in my Rhodes Scholar lectures, I always get one or two questions about the geologic timescale. So I'm going to start with this fun presentation of the timescale you see here. So this goes back to the early 1700s when geologists they didn't know how old any of the rocks on Earth are. And but they did know that they could relatively age rocks by what they called the law of superposition, which means that younger rocks fall on top of are formed on top of older rocks. So based on that law of superposition, they divided the Earth into layers of rock, and they gave those layers names that you see here on this graph of eras and periods, such as the Triassic and the Paleocene, Cenozoic, etc. They did this without knowing the age of any of the rocks or the age of the Earth. So what they did is they were able to take fossils in the rock, and based on the law of superposition, they could tell you the relative ages of certain fossils. For example, they knew that the first fishes appeared during the Ordovician period, and the first dinosaurs show up in the Triassic period, and the first human fossils show up in the Pliocene epoch. But again, they had no idea how old any of these rocks were. And then about 100 years ago, geologists learned how to actually determine the actual ages of rocks by studying the natural radioactive decay of certain elements in those rocks. So you can see the time scale on the right that indicates in millions of years the ages of the rocks. So today we know that the Earth formed about 4.6 billion years ago, and that the first fishes came along 470 million years ago, the first dinosaurs about 225 million years ago, and they became extinct about 65 million years ago. And finally, the earliest human fossils appear about 5 million years ago. So that gives you a sort of a frame of reference and a history of geologic time. Now let's look at the ages of rocks in Snow Canyon. We'll use the same graph for that. So first of all, the Jurassic and the Navajo and Kayenta formations were deposited between 200 and 180 million years ago at the earliest beginning of the Jurassic period. So fossils found in Jurassic rocks elsewhere, not in the Navajo Formation, but elsewhere on Earth, indicate that the Jurassic period in Navajo Sandstone was contemporaneous with an age of the dinosaurs, such as this carnivorous dinosaur Allosaurus I show here. But keep in mind, this animal did not live in the desert. Anyway, so what about the younger rocks? Well, you can't see the younger rocks because geologists know that about 5,000 feet of younger rocks once existed on top of the Navajo sandstone, but now they are eroded away as of today. So there are no younger rocks present in Snow Canyon, except for the 33,000-year-old Santa Clara lava flow. Below the Jurassic, Navajo, and Kayenta formations, there are 15,000 feet of older rocks that are aged, were deposited between the Cambrian age period, which was the period when almost all of Earth's plants and animals evolved, until the Kayenta formation. Those rocks, 15,000 feet of older rocks, and the oldest rocks, there's several thousand feet of older rocks in the crust, miles of crust, so they're all buried. So what you can see in Snow Canyon is simply the Kayenta formation and the Navajo formation and the lava. So where did the Navajo sand come from? Well, the short answer is from as far away as the Appalachian Mountains. So to explain that, we must go back 220 million years ago to the late Triassic period, just after the evolution of the first dinosaurs. And so at this time, this was the height of the amalgamation of the supercontinent Pangaea. all of the continents on Earth were amalgamated into a single landmass. Those landmasses were joined by two smaller landmasses to form Pangaea, one being Laurasia, which is North America, Europe, and Asia, and then Gondwana, which is Africa, Australia, Antarctica, and South America. So they were joined together by means of a huge collision along the black dashed line that you see there. And that collision of Laurasia and Gondwana to form Pangaea uplifted the Appalachian Mountains. This is very important because the Appalachian Mountains would become an important source of sediment for the Navajo Sandstone. Now we have zoomed in a bit on Pangaea, and we're looking primarily at Laurasia and even zoomed in mainly looking at North America. So, and this is 200 years later during the early Jurassic time. So here you can see the landmass is still together, but changes in the direction of those land masses had changed in the intervening 20 million years since the last map we looked at. And the two land masses are starting to split apart. They're separating or rifting, as geologists say, and they're moving away from each other along the line of the red dashes. As a consequence of that movement, the North American plate is drifting to the west and into a Pacific plate that is drifting to the east. And there they collided with each other to form a subduction zone. And so we're going to take a look at that right now. So this is the fundamental, one of the fundamental processes of plate tectonics. You can see the Pacific plate on the left. It's drifting to the east or to the right and into the oncoming North American plate that's drifting to the west. So what happens is as the heavier, thicker crust of the North American plate overrides the Pacific plate and creates the zone of subduction. The tremendous friction between the plates at depth, as you can see on the lower right-hand side of the photo, tends to melt the upper part of the oceanic plate and the lower part of the continental plate to form magma. And that magma rises to the surface. Most of it solidifies below the surface in below ground masses of magma called batholiths, that white feature on the right, but some of the magma comes to the surface as volcanoes. Just as important as that is that this collision of plates compresses the crust of the North American plate and it uplifts the mountains and some of the volcanoes. So you have a mountain range parallel to the North American continent, pretty much along the entire margin of that continent with the Pacific plate. So now we've zoomed in just on that part of North America and superimposed on here is a present day map of the United States of America. So on this map, you can see in the lower right-hand corner, there's the Appalachian Mountains. They were pushed up in the last 20 million years before due to the collision of the land masses. And so they're very high at this point. They're not the foothills you see today that I grew up with in Virginia. And also note that the Appalachian Mountains at the time extended a lot further southwest and into southern Texas at the time. Over on the far side, on the left side of this map, you can see the subduction zone that I showed you in the previous model, indicated by the yellow dashes. And that subduction zone lifted up the mountains along the margin of the North American plate. Outlined is the state of Utah, and the red dot in this particular map and all others that you will see is Snow Canyon. So it gives you a good picture of where we fit where we live today 200 million years ago at the beginning of the Jurassic period. So what geologists have learned is from studying the minerals, some of the very scarce minerals in the Navajo sand, is that much of the sand from the Navajo Sandstone and actually the Kayenta Formation, I spoke a little too soon. We're talking about Kayenta Formation right here. So a major river system indicated by the blue lines carried sediment, large volumes of sediment from the southern Appalachians across plains. And these were vast, featureless plains and into the area of Utah and into what I will describe later as a sedimentary basin. And other rivers brought even more sediment from mountains in southern New Mexico and southern Arizona. And all of those rivers you see indicated by the blue arrows that are known as the Kayenta River System to geologists. So this river system carried massive quantities of sediment, clay, silt, sand, eroded from the Appalachian Mountains and the other mountains along the southern perimeter of the United States of America, and transported those sediments via the rivers and many tributaries across these vast featureless plains into the sedimentary basin centered in Utah. The basin actually extended as far north as Wyoming and Idaho and well into Arizona. So let's look at this concept of the sedimentary basin because it's key to understanding the origin of the Navajo Sandstone. So we're going to look at a little bit different model of the plate tectonics and subduction. So we're showing the same, a different version of that. The Pacific plate is subducting beneath the North American plate. I'm only showing a slice of this whole subduction zone. It actually spanned the entire margin of North America. Anyway, so we already mentioned the uplift of mountains along parallel to the subduction zone and on the margin of the continent, the continental plate of North America. So in this model, those mountains were in Nevada. Interior of Nevada, what happens is that the tremendous weight of the mountains being uplifted, additional crust being created, causes a reactionary downward flexing of the Earth's crust interior to the mountains and forms a basin, which starts to subside as the mountains uplift. So as a consequence of that, the basin, which in this model is in Utah and Arizona, slowly fills with the sediment carried by the rivers that I showed you on the previous slide. Now, I need to make an important point about this because I get a lot of questions about this when I speak about it. So we're going to look at this model of the sedimentary basin. This is the same basin I showed you in the previous slide. Notice at the top, the mountains are in Nevada, and they're being uplifted because of the subduction zone, which is to the left of this diagram. That uplift puts a lot of load on the crust, and it creates a downward flexing of the crust to form the sedimentary basin. So as the mountains uplift, the basin subsides. And the deepest part of the basin throughout this period was in Utah. And but the basin extended, further into Arizona and New Mexico to some degree, and Texas was a long ways off. So these rivers emanated in Texas, but they're collecting sediment all along the way. So the rivers are bringing sediment as the basin subside and as the mountains uplift. The point I want to make here, though, is this, that the subsiding basin continued at about the same rate that the rivers brought sediment into the basin. And it's because of this fundamental dynamic of basins subsiding at the same rate as rivers bringing sediment that this basin could collect sediment for 160 million years, which is how long it lasted. And during that time, I think the deepest part of the basin is in Utah, and there was something like 26,000 feet of sediment at the bottom of this basin. So with that, we're going to zoom in one more time, and we're going to look at the southwestern US 200 million years ago. And we're going to go back, and this is when the Kayenta River system, and I'm showing you the Kayenta River system. Again, to remind you, it's bringing vast quantities of sediment from southern Texas across New Mexico, and rivers are bringing a lot of sand and sediment coming in from the southern mountains. So at the beginning of the Kayenta period, the climate was semi-arid. But as time went on, at the beginning at 200 million years ago, with the advent of the Kayenta River system, North America started drifting into the latitudes on Earth of the trade winds. It's called the trade wind belts. And it's very important because the trade wind belts is arid. Most of Earth's deserts on Earth today, such as the Sahara and the Arabian Desert, occur in the trade wind belt. And the trade wind belt is characterized by extreme aridity and also by very high winds. So because of this shifting of the continent, the sediment load coming into the basin, as you can see on this map, consisted mainly of sand, lots of sand. At the same time, other rivers were bringing sediment from highlands in Colorado and bringing a lot more sand. All of these rivers were carried into this basin for 10 million years by these river systems at a time when the climate was becoming more and more arid. By the end of the period, the climate was one of utter drought. So all the rivers that you see here began to dry up by about 190 million years ago. They dried up and became intermittent, which means they generally only flowed during the rainy season, all the while bringing lots and lots of sand. So then under the, because as the plate drifted into the trade wind belts, very strong northwesterly winds, strong and persistent, started to blow that sand back upstream and to deposit it on the extremely hot, arid plains of the Kayenta River system. And with that, we have created the Navajo sand erg. An erg is a dune field. So for 10 million years, these strong northwesterly winds, trade winds, blew sand to the southeast until finally, as you can see here, it overwhelmed the Kayenta River system. By the way, that Kayenta River system, I forgot to mention, is represented, is today, you can see it today in the Kayenta Formation. So here we have the Navajo erg, which geologists think today, I mean, from today's perspective, it was the largest erg in the history of Earth. It was a nearly continuous sand sea of sand dunes. So just to put that in perspective, I want to say that this sand sea or erg, sand dune field or erg, was not the largest desert on Earth. In fact, the Sahara Desert today is about 5 times larger. But the Sahara Desert is primarily gravel plains, salt pans, and mountains and plains. And only 20% of the Sahara Desert consists of ergs, and the ergs are separated from one another by the different gravel plains and mountain ranges and stuff. And in fact, the largest erg in the Sahara Desert today is about 120,000 square miles. The largest erg on Earth today is the empty quarter in Arabia, which is about 220,000 square miles. By contrast, this Navajo erg or dune field was about 800,000 square miles, the largest in the history of Earth. Okay, well, so now we know where the sand came from, and we know that the sand was brought by rivers from a large area across vast plains and to form the Navajo erg or the Navajo dune field. But how did that Navajo sand become rock? Well, the short answer is the erg was buried and then lithified. So we'll talk about burial first in a paleogeographic sense. So we're coming back to the Four Corners region, and the sand was deposited between 190 and 180 million years ago. So here we're looking at 180 million years ago at the Four Corners region and this incredible sand dune field. So what happened is after a period of a relatively short period of erosion, sea level began to rise globally due to climate changes. And these are global climate changes and over long periods of time, nothing at all equatable to what the global warming we have today. So anyway, as the sea level rose, the Pacific Ocean was able to gain access into North America and into the interior. So that by 175 million years ago, a seaway had encroached into North American interior and actually flooded the sedimentary basin. The same basin that was in which the Navajo erg had pretty much covered up. But remember, we still have subsidence. Even though, so all that 4,000 feet of Navajo sand, the top was always at sea level. So it's always being subsided, it's always being buried. So 175 million years ago, the Sundance Seaway, as geologists have named it, encroached into Utah and the basin to the north and flooded it. And for 15 million years, this seaway persisted in this region. But it was a time of fluctuating sea levels. Climates can change drastically in 15 million years, and that's what happened. So as climate changed during the 15-year period, sea levels rose and fell. And as they rose and fell, the Sundance Seaway would retreat to the north when sea levels fell, and then would advance to the south when sea levels rose. And in this manner, this Sundance Seaway retreated back and forth across southern Utah for 15 million years, several times. During that time, the rivers brought sediment into the seaway, and as a consequence, mud was deposited in the center or the deeper waters of the seaway. The margins, as you can see around here, were vast, very, very large scale, vast flat mud flats and silt flats. And then so the mud in the middle of the seaway and the salt and the mud flats and silt flats around the margin for 15 million years. And then occasionally dune fields would grow on the margins, the eastern margin of the seaway. Such as this one here. This is about 170 or 65 million years ago. Another dune field formed called the Entrada erg, represented by the Entrada Formation today. Because of this Sundance Seaway, thousands of feet of sediment were deposited on top of the Navajo Sandstone. It wasn't washed away, it was buried. And in our area here in southwestern Utah, there are about 1,000 feet of Middle Jurassic Sundance Seaway sediments on top of the Navajo Sandstone. Well, eventually, oh yeah, I wanted to show you this too. So here's a larger scale view of North America that shows the Sundance Seaway. As you can see, it is believed to have encroached into the interior in Alaska, formed a long, narrow seaway until it gained access to the sedimentary basin and flooded it. So the basin was mainly Wyoming, Montana, Alberta, Utah, and Idaho, and about half of the Dakotas. 15 million years, finally went away. Well, it turns out that wasn't the biggest seaway. So we're going to fast forward now 115 million years ago. Another seaway encroached into the interior sedimentary basin. And this one was much larger, as I'll show in a moment. But in Utah, we're showing it here at its greatest extent. So the western shore of the seaway never quite made it to St. George area where we are. But what did happen was those high mountains in Nevada and Arizona were shedding sediments due to weathering of the rock and erosion of the rock, which means bringing the sediment down. And it accumulated in great thicknesses on the plains adjacent to this western interior seaway. So in this manner, where we are living today, where Snow Canyon is, about 4,000 feet of these mountainous sediments were deposited on top of the Sundance Seaway sediments, and bringing to a total of 5,000 feet of sediment on top of the Navajo Sandstone, or the Navajo Sand Sea, the earth, which was buried beneath that. So the bottom, so with 5,000 feet of sediment, of younger sediments on top of it, the very bottom of the Navajo sand was 9,000 feet below, below the surface, which causes a lot of changes to the sediment, as we'll see in a moment. So here's a part of my spelling of Arctic. I left out the sea, but there's the Arctic Ocean. So the seaway encroached from the Arctic Ocean southward and gained access to the middle, what was left of the sedimentary basin, which had expanded quite a bit by this time. And then at the same time, another seaway encroached northward from the Caribbean Sea, and they met in the middle and formed what's called the Western Interior Seaway. Geologists believe this is the largest seaway in the history of Earth, meaning an intrusion of the sea that splits a continent in half. So this seaway persisted from about 115 million years ago to about 80 million years ago. One thing I want to point out about this is if you notice the long shorelines of the Western Interior Seaway, spanning from the Arctic Ocean down in the Caribbean, well, those shorelines occurred during a humid climate. And what happened is by this time, the continent had drifted out of the trade winds belt and was moving more into the temperate latitudes and with more humidity. So there was lush vegetation along both shores of the Great Western Interior Seaway, and it provided a fantastic habitat for all kinds of marine and land animals and plants, especially dinosaurs. And so this is the reason why many of the world's greatest dinosaur fossil beds are found in Cretaceous rocks today, stretching from Arizona to Alberta. So eventually, around 65 million years ago, 60 million years ago, tectonic forces on the margin of North America terminated the subsiding basin. And so as a consequence, sedimentation stopped. The rivers found outlets to the ocean rather than collecting sediments in Utah, centered in a sedimentary basin in Utah. But still, after the end of the Cretaceous, we have the Navajo Sandstone, the Sandsberg, there below 5,000 to 9,000 feet below the surface. So this is a view of what happens in that sedimentary basin to the Navajo sand as it's being buried. So starting from the upper left, when the sediment, the sand grains are carried into the basin, they don't stick together. They're just loose sediment. But often there's groundwater, but they're loose sediment. As the younger sediment comes in, it greatly increases the overburden pressure on the sediment as it's being buried. So compaction occurs, in which case much of the water, not necessarily all of it, but much of the water is squeezed out of the formation as it gets deeper and the grains become compacted, tightly compacted. And then over hundreds of thousands or millions of years, with the addition of even more sediment and overburden pressure, the grains become cemented together. And the cement is usually it's derived from minerals that are left behind by the groundwater. And those minerals cement the sand grains together to form rock. And this process is called lithification. So rock is lithified sediment, and in the case of the Navajo Sandstone, it is lithified sand. Okay, so the last chapter of my presentation is how did the Navajo Sandstone get back to the surface? Well, the short answer is uplift of the crust and erosion. So what we're going to do is we're going to fast forward a long way. We're going to come all the way from the end of the Cretaceous period, about 60 million years ago, when the subsiding basin was terminated due to tectonic changes along the margin of North America and the United States. So this is a paleogeographic map of the Four Corners region during the Miocene period 15 million years ago. So during that intervening 50 million year period between the end of the Cretaceous period and the Miocene period at 15 million years ago, the Western United States, after the subsiding basin terminated, was gently uplifted. Here and there at different rates, different elevations, but overall the entire margin of the United States was uplifted well above sea level. Remember, this subsiding basin for 160 million years was at sea level. So now here we are 15 million years later, and you can see a map showing, and this is above sea level. Anyway, what happened was as the Earth was rising up, the continental plate, North American plate, became fractured into pieces, let's say. And so one portion of the plate, known today as the Colorado Plateau, was uplifted several thousand feet in such a manner that the horizontal sedimentary formations, including the Navajo Sandstone and the Kayenta Formation, were not folded or faulted or any other way modified in their basic shape relative to the regions around it. The regions around it, on the other hand, were highly faulted, highly folded, and crumpled, so to speak, into mountains and highlands. And I think you can see that on this paleogeographic map. You notice the Colorado Plateau, the red outline, sort of defines a basin, doesn't it? It's a relatively broad and flat landscape relative to the surrounding regions, which indicate highlands and mountains. So this Colorado Plateau was uplifted in such a way that this large flat surface existed 15 million years ago. So at that time, 15 million years ago, there were drainages on the Colorado Plateau, but they all all the drainages flowed interior. They all flowed inward. And what I'm showing you here is a representation, a theory, so to speak. It's not the only one, but it's a representation of the Proto-Colorado River, which you can see a portion of it here, was short at the time, and it was sluggish. And it flowed into a sizable lake. In fact, there were several lakes scattered about on the Colorado Plateau during the Miocene time. And so the Colorado River was a slow-moving stream and flowing in the direction it does today into this lake. Otherwise, none of the water or the rainwater collected on the plateau drained away from it, at least not in any significant manner. So from 15 million years ago, from that period until 5 million years ago, what happened was Southern California and Nevada and Arizona underwent some extreme tectonic changes and dropped. They fell away from the rest of North America downward about 4,000 feet. There's no way I could show this. I couldn't come up with a way to show it. But if you look at the Colorado Plateau, on here, the red outline, everything to the left was downfaulted, dropped about 4,000 feet relative to the Colorado Plateau. At the same time, a Southern California river system, a drainage system, started to form on the margin of the Colorado Plateau and was collecting the rainwater and forming a drainage system, collecting water from the plateau and carrying it southward. What happened is eventually, over about a 10 million period, from 15 million years ago to 5 million years ago, that river, its headwater started cutting into the flank of the Colorado Plateau. It was incising a canyon into the flank of the Colorado Plateau. And eventually, that canyon reached the surface of the plateau and it captured the Colorado River. So I'm going to show that on a diagram I invented. So this is a block diagram of the Colorado Plateau. You can see the highlands on the western margin. You can see the Proto-Colorado River flowing westward into the lake on the top of the plateau. That leaf-looking thing there, that's actually a canyon. So that's the headwaters of the Southern California River as it's carving a canyon into the headland, into the highlands. And remember that the plateau is 4,000 feet higher than the Basin and Range province that had dropped down in Southern California and Nevada. So now what happened was eventually that river cut through, and it cut its way all the way through the highlands to the top of the plateau. And by means of this canyon, it captured the Colorado River. When it did that, that sluggish Colorado stream or river was subjected to a 4,000-foot gradient from the top of the plateau down to the Gulf of California, which is the water that separates Baja Mexico from mainland Mexico. It exposed that plateau, the Colorado River, to that gradient. So now the last map I'm going to show is the present day geography of the Four Corners region, and there's the Colorado Plateau. So what this shows right now, 5 million years ago, you can see that that is the actual California River as it looks today. And I'm showing it just at that point where it cut into the top of the Colorado Plateau. Once it did, it captured the Colorado River. And soon after, the Colorado River captured all of the tributaries and streams on the Colorado Plateau. When that happened, it subjected the Colorado Plateau to raging rivers and streams because of the 4,000-foot gradient to get down to the Sea of Cortez, caused these streams to flow at much more rapid rates. As a consequence, the downcutting of these rivers increased dramatically throughout the Colorado Plateau. And as a consequence of that, there was extreme erosion, unlike ever seen in this area throughout the Colorado Plateau, downcutting and erosion. And so the consequence of this erosion over the last 5 million years is that the Colorado River and its tributaries and streams have created the largest, most beautiful, fantastic landscape of mesas and buttes, of cliffs and of hoodoos anywhere on Earth. And it is also the reason that we have Snow Canyon today. It is the same processes. So the vast erosion due to the capture of the Colorado River in 5 million years not only created canyonlands that you saw in the previous photo, but it created the eroded landscape that we enjoy today in Snow Canyon. That's it. It's a short presentation, and I'll be glad to entertain questions. And I'm not sure how that will work, but I think Barry's going to supervise that.
Barry, you gonna unmute?
Yep, you guys, if anybody wants to ask a question, I have muted everybody prior to this, but you're welcome to unmute or hit your space bar and ask George a question. Okay.
Okay, no questions?
Trying to get
Did everyone get it?
Thank you, George.
Okay, you're welcome.
I'm seeing a lot of thumbs up, George,
Yeah.
which I read as thank yous.
Yeah,
Okay,
Lots of thank yous, lots of thank yous.
good, good.
That was very interesting, George. Thank you so much.
Oh, you're welcome. You're welcome.
That's
Stay on.
We're very glad to have you join us, and we'll be presenting more of these presentations, and we have about 3 or 4 more scheduled for the rest between now and May. Now and the end of May.
Nice.